Hello, welcome to another lecture. We're going to go over superposition and standing waves in chapter 16, continuing our discussion on wave phenomenon. And now we're going to really talk about what happens when multiple waves are present at the same location. We're going to use the idea of superposition to understand the phenomena of interference of waves and what standing waves are. So let's talk about the principle of superposition. You might recall it from Physics 1, and we used that principle to be able to add vectors together. Let's think, physically first in a very straightforward application of when two objects are present at the same time. For example, two baseballs. So let's say we throw them from a pitching machine and we point those pitching machines together. Well, there is a location where those physical objects will meet and they're going to interact with each other and bounce off of each other, right? So this is kind of an example of superposition, but what it's meant to do is it's meant to illustrate what waves don't do. So when waves interact with each other, they don't interfere. This is meant to illustrate a physical property of objects that we know and understand. However, waves behave differently. So if we kind of set up the same scenario and instead emit sound waves from two speakers, right? Those sound waves are going to emanate in a circular wavefront away from the speaker face. And what I mean by that is there's going to be multiple sound waves coming out of the speaker. Well, some of those are going to eventually interfere with each other. For example, if we select these two waves right here. What happens when they meet is different than what happens when physical objects meet together, right? Physical objects like a baseball, when they meet in the same location, they're going to bounce off each other, but sound waves are just going to cross each other and continue going on their merry way. What happens at that location where they meet is where the principle of superposition comes in. We are able to consider those two waves as simply the addition of one to the other, and that displacement sum is going to be what is happening at that location. So what do I mean by that? The principle of superposition is when two or more waves are simultaneously present at a single point in space. And the displacement of the medium at that point is going to be the sum of the two displacements due to each individual wave. So here we can see a physical wave from a wave on a string, right? Two of them. So imagine we take a string and we shake either end at the same time. So we're going to have a wave pulse moving to the right and a wave pulse moving to the left. Well, eventually they're going to meet in the middle. And the way that those waves interact is they simply add together. So the two crests are going to add together at the center and overlap and create a displacement that is roughly twice the amplitude of each wave. So after they interact, they're going to keep going on their merry way as if nothing happened, right? They're going to roughly maintain the same amplitude. So we can look at that by using our snapshot graphs. So here we have a snapshot graph and we see two wave pulses moving towards each other, a triangle wave pulse and a rectangular wave pulse, and they're both moving at the same speed. What happens when they approach each other is they begin to add together, right? So if we go to this next slide, about 2 seconds later, those wave pulses have met. And the wave that is present at that location is simply the sum of those two displacements. So you can see here that the triangle wave is being added to the rectangular wave and creating a much larger and different shape combined wave, right? Simply by adding them together. And so when the waves add together and create a positive displacement or a displacement that is, you know, larger than it was before, we call that constructive interference. Destructive interference happens when two wave pulses meet that have equal and opposite amplitudes. So let's take a look at this example here. We have a positive triangle wave pulse. We have a negative triangle wave pulse. They're both moving at 1 meters per second, and they're going to approach each other. Well, when they start to approach each other, we're going to begin adding the displacements. And there's going to be a time where this total displacement is going to be 0, right? It's going to be the time when the positive wave pulse lines up on top of the negative wave pulse. And of course, if you were to add those two values together, you would get +1 - 1 = 0. Now, when those waves continue to move, right, they're unaffected by that addition. They're going to keep moving, and they're going to separate from each other and look the same, right? Nothing has changed. This is still a negative wave pulse moving to the left, and this is still a positive wave pulse moving to the right. So this is called destructive interference, where the waves overlap and their displacement is less than either individual displacement. So what is a standing wave? Let's talk about that. Standing waves, they look like they're not traveling anymore, but they are made of traveling waves. Standing waves are created when individual points on the string oscillate up and down, but the wave itself does not appear to travel. It appears to stand in place as it oscillates, and we saw an example of this in lecture, right, where we had a wave on a string, and it's clamped over here on the right, and then it's clamped over here on the left because it's attached to that mechanical vibrator. And so the wave is being trapped, right? So the mechanical vibrator is creating a wave moving to the right. Well, that wave is going to encounter this barrier here, and it's going to turn around and be reflected and move to the left. And that is going to repeat itself back and forth, back and forth. And at certain frequencies, you will get what looks like a standing wave pattern. Superposition of waves is what creates a standing wave. So this is just a very simple, setup here. Again, we're gonna shake the rope, and we're gonna create two waves moving in opposite directions by shaking one side of the rope and shaking the other side of the rope at the same time. And so superposition is gonna occur, right? Because we're going to be adding the displacements as those waves interact with each other. So how do we turn two traveling waves into a standing wave? Well, there are certain conditions between the two waves that will create a standing wave, and we'll talk about those conditions. If those conditions are met, you get a traveling wave. And the way you can see that is by looking at the time dependence of the wave that is moving to the left and the time dependence of the wave that's moving to the right, and looking at the sum of those two. So if you take a look at this graph here, the wave moving to the right is represented by the red line. The wave moving to the left is represented by the orange line, and then their superposition is represented by the blue line. So at certain times related to the period, okay, you're going to see that how they add up together, right? And at a 1/8 of the period, you're going to have a very clear wave pattern here, right, where they those waves add together and create a constructive pattern, right, constructive interference. And then at other times, you're going to have, let's say at 3/8 of a period, you're going to have a moment where they actually all add up to 0, right, where you have destructive interference. And so here is a schematic which just shows that superposition instead of also the left and the right wave. And so, in other words, when you have two traveling waves interfering with each other, they turn into a standing wave because some points will always cancel, okay? For example, points occurring at a time that is 3/8 of a period. And then you have some points that always add to a maximum displacement, okay? For example, at this time. So we have our standing wave pattern, and we have determined that there are some points that never move, and there are some points that have maximum displacement. Well, we have names for those. The points that never move are the points where the displacement appears to be zero, and we call those nodes. The antinodes are halfway in between the nodes, and these are locations where maximum displacement occurs. And you can see that there is a relationship between those locations and the wavelength of the wave. Nodes and antinodes are always spaced half a wavelength apart. Nodes are the points that always cancel, and antinodes are the points that always add up to a maximum displacement. So let's look at that wavelength relationship. The wavelength of a standing wave is twice the distance between successive nodes or antinodes, right? If this is half a wavelength, well then the wavelength of a standing wave is twice that, right? So if we were to monitor the intensity of those waves as a function of position, what you would see is a maximum intensity at the antinodes and a zero intensity at the nodes. These intensity maxima are going to be half a wavelength apart because they correspond to the antinode locations. So let's see if we can figure out what the wavelength of this standing wave is. You might recall from what we just talked about that the distance between nodes, or the distance between antinodes, right, nodes here, antinodes here, is half a wavelength. So we can simply find that distance, which is half a meter, multiply it by 2. The wavelength is 1 meter, right, according to that concept. Another thing you can do is you can certainly trace one wave out of here, right? So if we start up at a maximum here, and then when we return to that point, that's going to be 1 wavelength. And as you can see, that equals 1 meter. Let's talk about standing waves on a string, and then we'll talk about standing sound waves. We need to understand what is happening when a standing wave is created on a wave on a string. And so what's happening is we have one source of the wave, right? And that's the mechanical vibrator that's jiggling the string up and down. So we have a wave coming out of that mechanical vibrator, and it's moving to the right, and it's going to encounter a boundary where that string is clamped down. And so this is an illustration of that boundary. Okay, it's kind of like attaching the string to a wall. So when the mechanical vibrator sends out a wave, right, we have a positive wave pulse moving to the right. And when it hits the boundary, what happens? The wave actually gets reflected and inverted, right? The wave obviously gets reflected because it starts moving to the left, but something else happens. The amplitude of that wave kind of gets multiplied by -1, right? It's inverted. The amplitude value itself, right, does not change. It's still the same amplitude, but now it's a negative amplitude. Inversion happens when the boundary prevents displacement. Here, when that wave meets that point of the string that's attached to the wall, it cannot shake the wall, right? The wall is too heavy, it's too large to get that wall to move up and down. And so what happens is the wave instead needs to turn around and head back, and it produces an inverted wave. So this can happen not only with a boundary, but this reflection can happen with a discontinuity. So what I mean by discontinuity is, let's say we start with a thick rope and then it's connected to a thin rope. Well, if we send in a wave pulse to the right, and when it encounters this thinner rope, there is going to be a reflection and a transmission. The reflection this time is not going to invert the wave pulse, okay? This is because the boundary allows displacement, right? This is not a solid object. This is just actually a thinner string, which is much easier to shake, right? So that original wave is going to keep going through. Some of it is, and some of it is going to get reflected, and you can see that the amplitude is going to get split. Here's another version of that. Let's say we start off with a thin string and it meets a discontinuity where the string gets thicker and heavier or more massive. Well, then it's going to act as a full hard boundary where the wave pulse gets inverted. But because it's not a completely solid boundary and a little bit of displacement is allowed to occur, some of that wave is going to be transmitted, right? So inversion happens when the boundary prevents some displacement. You can create a standing wave, a couple of different ways, right? You can attach, your mechanical vibrator or your hand and shake that string on the left, and it's going to bounce off, it's going to go this way, bounce off the boundary and come back. Or you could wiggle the string in the middle, and that would create two waves moving to the left and to the right, which would meet these boundaries and turn around and come back and interact with each other. So those are both equivalent ways of creating standing waves. What you saw in class, a demonstration, or taking the string and wiggling it in the middle. What's happening is the reflection of the boundary is causing the waves to meet up again, and therefore applying the principle of superposition would show a standing wave pattern depending on the frequency of the wave, which is what we'll talk about very shortly. So when I demonstrated this in class, I changed the frequency of the function generator that controlled the vibration frequency of the mechanical vibrator, and I showed you 3 different standing wave patterns. These patterns are called modes, and they are denoted by integers. So mode 1 of a standing wave looks like this, okay? You have 1 antinode and 2 nodes. Mode 2, so let's say I increase the frequency a little bit more. Mode 2 is going to have 2 antinodes, 3 nodes. So this mode number is related to the antinode number. And you will always have one more node than you do antinodes. So these are some of the patterns that you should be thinking about when you are considering standing waves. So let's talk about those special conditions. First, let's look at the wavelength of the wave. The wavelength of the wave is going to depend on what mode you're at, right? So the wavelength of the wave has a formula of 2 times the length of the string divided by what mode you are at. And so you can see that depending on the mode, you're going to have a different wavelength. And so you can kind of count the wavelengths, right? You know that a wavelength, is the distance. The wave is from, peak to peak, trough to trough. It's also from 0 to 0, but you need to make sure when you're counting your zeros that it's the same 0, the increasing 0, right? You're crossing 0 on the increasing direction, not the decreasing. And so when I take this bottom piece of the standing wave and I map it out here, you can see that that is one complete wavelength. And so you can see one complete wavelength for m equals 1 is 2L over 1, which is simply twice the length of the string. Let's look at mode 2. The wavelength of the standing wave here is simply going to be the length of the string because I am able to count one wavelength here, right? And that one wavelength fits in the length of the string. Finally, mode 3, the wavelength is 2/3 of the length of the string. And so let's see if we can see that. Here's one. There's one wavelength, right? And it fits into 2/3 of the length. Standing waves can exist on the string only if the wavelength of that wave is one of the values given by this equation here. We can convert that wavelength into a frequency by using the fundamental wave equation. We take the wavelength and set it equal to velocity over frequency, Remember, the velocity is constant, right? The velocity is a constant. And what is it given by for wave on a string? The tension over the mass per unit length. So we can express the frequency in terms of, by substitution, V over lambda. And so when we do that, you can see that the frequency of each mode is the mode number times the velocity divided by 2L. These are the frequencies that produce the modes, the standing wave modes on a string of length L. And so what you saw me do in class is I had that little function generator and I spun the little dial and I increased the frequency until I reached any of these values, okay? Any of the values of frequency that match V over 2L times M. So if the mode number is equal to the number of antinodes, what's the mode number of this standing wave? That's really easy. 1, 2, 3, 4, 5, right? 5. So what do we call these frequencies as a function of modes? They have a special name. They're called the harmonics. So the first mode of a standing wave, when m equals 1, is called the fundamental frequency. All other modes are multiples of this fundamental frequency, and they are called the higher harmonics. So F2 would be the second harmonic. F3 would be the third, and so on. They're all integer multiples of the fundamental frequency. So let's do this example. We have a 2.5 meter long string vibrating at a frequency of 100 hertz. And there are 2 nodes positioned at 1 meter from one end of the string and 1.5 meters from that same end of the string. No points in between those 2. Which harmonic is this? What is the string's fundamental frequency? And what is the speed of the traveling waves on the string? So let's write down some equations that we know. We learned that the wavelength of the standing wave depends on what mode, and it's equal to twice the length of the string divided by that mode. We also learned that the frequency of the standing wave also depends on the mode, and we were able to convert wavelength to frequency using our wave equation, which made the fundamental frequency equal to the mode times the velocity over 2L. What we also know is we know something about the spacing between nodes. We know that adjacent node antinode distance is equal to half of a wavelength, which would make node to nodes one wavelength So if we have adjacent nodes at basically half a meter apart, we know that the wavelength of that standing wave is half a meter. But we don't know what mode that is, right? So we can solve. We know that the wavelength of our, this is a meter, this is a unit, okay? This is the unit M, is equal to 2L over our unknown mode. Well, we know what L is, so we can solve for that mode, right? 0.5, I'm gonna drop my units just for clarity here, is 2 times 2.5 over M. 0.5 is equal to 5 over M, and therefore M is going to be 5 over 0.5, which happens to be 10. So we're at mode 10 here. So this is gonna be the, which harmonic is it? It's going to be the 10th harmonic. we can find the string's fundamental frequency since we know that M is 10. Let's start off, the 10th harmonic is equal to mode 10 times the fundamental frequency. So the fundamental frequency is going to be the 10th harmonic divided by 10. So that 10th harmonic is the 100 hertz, right? So the fundamental frequency is going to be 100 hertz divided by 10, which gives us a fundamental frequency of 10 hertz. So that's the fundamental frequency. Let's highlight our answers. Our mode is 10, 10th harmonic. What is the speed of that wave? The speed of the wave, which highlighter color we can use? Green. Let's use green. What's the speed of the wave? The speed of the wave we can figure out by using the fundamental frequency, right? So we know that the fundamental frequency was 10 hertz. And we know that the fundamental frequency is equal to 1 times the velocity divided by 2 times the length of the string, just 2.5 meters. So we can solve here for the velocity. And what we get is 5 meters times 10 hertz, which equals 50 meters per second, right? Because hertz is inverse seconds. This is a very, very good example, which will get you comfortable with the relationships of standing waves. I recommend doing this example again later on, once it's left your memory. We have a couple more examples, one more here. I encourage you to do those on your own in preparation and while you're studying, so DIY. So this is a slide that is, bouncing off of what I was just saying, right? The fundamental frequency is related to the speed of the wave on the string, and we know that the speed of the wave on the string is related to the tension and the mass per unit length. So when you pluck a string on a string instrument like a guitar or a ukulele, even a piano, you are sending a wave pulse down, and that wave is going to travel at a speed that is determined by the properties of that string. Well, depending on the length of the string, you're going to achieve a particular frequency of sound, right? And so you can tune your instrument, changing the fundamental frequency by changing the tension on the string, or perhaps replacing the string with a different mass per unit length. So this is just kind of relating what we're learning about to practical, musical instrument theory. This is a great example problem. I was saying there was a few. To do this one is going to relate a little, it's going to kind of throw a little bit back to physics 1, where the tension on the string, and I'll give you the hint, the tension on the string is related to the mass times gravity of what is pulling down and creating the tension on that string. So in other words, here you're going to use your physics 1 knowledge to determine that what the tension in the string is, which is simply mass times gravity. So let's talk about sound wave. We create music, we have stringed instruments, and we have wind instruments. So wind instruments take advantage of standing sound waves. So let's talk about that. They're a little bit different. So standing sound waves are longitudinal pressure waves. Longitudinal waves means that what's changing and what's getting disturbed is occurring along the same direction that the wave is traveling. And so for sound, what's changing is the density of the particles in a certain space. And so you're creating different regions of compression, regions of high pressure, high density molecules, and regions of rarefaction, which are low density, low pressure molecules. And so to create a standing sound wave, you need to be able to trap the sound. okay? You can't let it go in 3 dimensions. You got to trap it in a tube, just like in a string, we're trapping the wave in 1 dimension to move along the string. So we're going to trap sound in the tube. And what, particular frequencies of sound that you put into the tube, you could get standing wave patterns. And they're going to follow the same mode and antinode patterns that you saw in the previous examples. So what's different though is what conditions are going to cause a reflection with inversion or not, okay? So that's what's different here. And that's because what's being displaced in a sound wave is the pressure. So take a look at this graph here. What we're plotting on the y-axis is not displacement, it's pressure, okay? And let's take a look at a tube that is open at both ends. So if you have a tube that is open at both ends, each end of that tube that's open is exposed to atmosphere of the room, okay? And so that openness is actually going to act like the clamp in the string situation, okay? Why does it do that? Why is the open acting like the clamp? Well, that's because at the opening, the pressure in that tube must equal atmospheric pressure. So we're forcing the condition. We're not allowing the pressure to vary. Just like at the boundary, we're not allowing the displacement of the string to vary. And so the openness of the tube is going to act like a clamp on the string, and you're going to have a node at the open end of a tube, okay? So nodes appear at the open end. So here is a plot of the open tube. You're going to have 3 different tube configurations: open, 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 closed, and closed, closed. So when you have an open tube, the pressure at the ends, which are open, is forced to be a specific value equal to whatever the pressure of the room is, hopefully 1 atmosphere. Okay, so although higher pressure doesn't really hurt us too much. I don't know if you've heard of a hyperbaric chamber. You sit in a high pressure area, and that is supposed to like promote healing and stuff. So it's not, we can obviously survive in higher pressures, but not too high. So anyway, we clamp down the standing wave, the standing sound wave at the open ends. All of the same relationships still hold. So the distance between node and antinode is still half a wavelength. All right. And we still have all those relationships, but now it's kind of like we've flipped the where the node sits and where the antinode sits. So let's look at a closed tube and an open closed tube. So in a closed tube, both ends are closed. And so opposite to an open end, a closed end is going to act as an antinode. And that's because when the pressure wave meets the wall, it gets inverted. And it turns around and heads the other way, right? It gets inverted. It goes from a positive to a negative amplitude. And so for a closed tube, the antinodes occur at the ends, and the nodes will occur half a wavelength away. For an open closed tube, well, one side is going to be the node, the open side, and then one side is going to be the antinode, the closed side. So you're going to have a different relationship for open closed. We're going to talk about that. The open and the closed tube are going to look a lot like the standing wave on the string. The wavelength is going to be equal to twice the length of that tube divided by whatever mode you're at. And then we use our fundamental wave equation to convert between lambda and frequency, and we get the exact same equation that we saw for standing waves on a string. However, the open-closed tube has a different relationship. And that's because if you look back up here, the open side has your node, the closed side has your antinode. It's not symmetric. And so the wavelength then is going to be 4 times the length divided by the mode number. And then we use our same relationship to find the fundamental frequency. And so what you can see here is that in order for this relationship to stay true mathematically, you can only have odd modes appearing for the open-closed tube. Only odd modes, right? Because if you were to put m equals 2, well, then you would end up with a wavelength equal to a wavelength of the closed, closed, or open, open. So only odd number modes are permitted. So this compares the different standing waves that appear on each type of tube. And we can, analyze these, in more detail when you get to a problem. Okay, so for now, us talking about each one, I don't think is going to be super beneficial. We can refer back to them once we get a problem. Here's one. We have an open tube, and the length of the tube is L. Which graph would show the third standing wave, the third harmonic standing wave in this tube? So first of all, because it's open, we know that we're going to have nodes at each end. So we can immediately rule out B and D, okay? And mode number 3 is still going to be indicating the number of antinodes, just as it did for standing wave on a string. So 1, 2, 3, we're going to have 3 antinodes. So A would be the best choice, the only choice here. Okay, summary. Wave on a string, open, close, all have the same formulae. What's different is the open-closed tube, the symmetry, right? There's no symmetry there. And so you're going to have a slightly different formula for the wavelength and the frequency. And you're also going to note that the modes are only odd numbered. This is a problem-solving strategy that if you are doing some practice problems and you don't know where to start relating to sound waves, just go step by step. And I encourage you to do that if you are one of those people that just stare at a problem and you just get real lost in your anxiety. Okay, there is a method to the madness. Okay, refer to these. So let's take a look at this example and see if we can tackle this. So this is a picture of your ear canal and your eardrum. The eardrum transmits vibrations to the sensory organs of your ear, okay? The figure shows the adult ear canal is roughly 2.5 centimeters long. And so the question is, what frequency of standing waves would occur within the ear canal that are within the range of human hearing? And so they give us the velocity of sound in the warm air of the ear canal, right? Because inside your ear canal, inside your body, you are not at room temperature or else you'd be dead, right? You are a little bit warmer than that. And so instead of 343 meters per second, the velocity of the air in your ear canal is about 350. It's a little bit higher. So the boundaries of human hearing, the frequency range, right? Remember, went from 20, let's say the lower end was 20 hertz and the upper end was 20,000 hertz. So we want to find what the frequencies of standing waves that can occur within those bounds. We know that the length is equal to 2.5 centimeters. So our equation, right? our fundamental frequency and modes, harmonics of frequency, it's going to depend on what kind of tube this is. And so the eardrum is a boundary. And obviously the exterior opening of the ear is open. So this is going to be an open, closed tube. So we know that the frequency is going to be equal to the mode times the velocity divided by 4L. We can check that. Up here. So all we need to do is find out what frequency of standing waves can occur within the ear canal. And so we'll just cycle through the modes, right? Starting off around 20 and stopping when we get to 20,000. So let's take a look at mode 1. And let's make sure that we report this in meters, which is 2.5 centimeters is 0.025 meters. So the frequency of mode 1 3,500 hertz. Frequency of mode 2 well, it's going to be 2 times 3,500 hertz, right? Which is 7,000 hertz. And then we're going to do 3 times 3,500 hertz. 3 times 35 is 10.5. So we have 10,500 hertz. And so on and so forth, right? Until we get to about 20,000. We're going to stop. So those are the frequencies at which we can achieve standing waves in the ear canal. So the last section we're going to talk about is the interference of waves from 2 different sources. We looked at standing waves, and standing waves were essentially one source of the wave, and it was interfering with itself after it reflected off of a boundary. And so we're going to kind of get a little bit more general and look at what happens when you have waves interfering with each other from 2 different sources. The first geometry we're going to look at is the interference of waves along the same line. And so you're going to have speakers creating a source of sound, right? A source of waves, one behind the other. And let's say that the speakers are 1 wavelength apart. Okay, the distance between the speakers is equal to the wavelength of the waves that they are emitting. And so when that happens, you draw your waves, right? Let's get red. 1 coming from speaker 2, and then the other wave coming from speaker 1. And if the waves coming out of the speakers are identical, what you will see is that when they are spaced, when those speakers are spaced a wavelength apart, everything's going to add up, right? You're going to get a peak, a super high peak, a super low trough, and your zeros are going to add to 0, right? Everything's going to add together, and you're going to get a wave that is a superposition of two equal waves. And so what's happening here is that the waves are constructively interfering. They're constructively interfering. And what we say is that those waves are in phase with each other. Okay? They're in phase with each other. When the crests and the troughs are aligned, those waves are in phase with each other, and you will have constructive interference. So in other words, if the distance between the speakers, we are going to call the path length difference. If the path length difference or distance between the two speakers is equal to a wavelength or a multiple of a wavelength, then the two waves will be in phase and will produce constructive interference. Any whole number, any integer multiple of wavelength. If their path length difference is any integer multiple of wavelength, they'll get constructive interference. Now, what happens if we, let's say, change the distance between those two speakers to half a wavelength? Well, if you draw your waves like we did before, what you'll see is that the waves are going to add up to 0 because the peak will be aligned with the trough of one wave, and the trough of the other wave will be aligned with the peak of the other wave, right? So they're all going to add up to 0. And so these are out of phase. Those waves are out of phase, and you will get destructive interference. The two waves will be out of phase and produce destructive interference. And that occurs when the path length difference is equal to a integer plus half number of wavelengths. So these are the conditions that produce constructive and destructive interference. We determine it based on the path length difference, right? The difference in travel that each wave experiences. That path length difference is equal to a whole number of wavelengths, then you got yourself constructive. If it's equal to an integer plus a half, then you have destructive interference. So here we go. This is the quick check problem that gave us some issue. And I will take some blame, okay, but not all. So let's draw the wavelength of 4 coming out of the left speaker with red. And if the wavelength is 4, if we start off at 0, that means we're going to end at 0 increasing. So we're going to do that again. Okay, so there's our wavelength at 4 coming out of the left speaker. The wavelength coming out of the right speaker is going to start off as increasing just like it did for the left speaker because these are identical waves. And when you draw that out, what you see is completely destructive. And so you might be wondering, why is the math, right? So let's say we were to do the math behind this, and at point A, we have one path length of 2, another path length of 6, why 6 minus 2 equaling 4 meters does not give us the constructive interference of m times 4 meters, or m equals 1, right? The math tells us constructive, but the picture tells us destructive. And the missing piece here is that when the waves are not traveling in the same direction and they're traveling towards each other, there is an additional phase shift due to the propagation direction. And so that can be illustrated if we write an equation for the wave coming out of the left speaker, a cosine lambda x over lambda minus t over period, right? That is for a wave moving to the right, and we know that a wave moving, that should be wave moving to the right, which is the left speaker. Okay, a little bit confusing in the notation, right? Left speaker, where the wave is moving to the right. And we know that there's a minus sign, right? We talked about that in the previous slides. And then we have our wave equation for the wave moving to the left, coming out of the right speaker. And the only difference is a plus sign in the argument. So to know if there's a phase difference between those two waves, we subtract the arguments from each other. So we would have x over lambda minus t over tau, or period, minus x over lambda plus t over period. And the subtraction of those gives you, right, these terms go away, and it leaves you with a negative 2t over tau. So there is indeed going to be a phase shift here due to the fact that the waves are moving in opposite directions. And so when you apply your constructive or destructive interference, you are assuming identical sources. So what I'll tell you, I just wanted to explain this to you. What I'll tell you is that on the exam, I will not be including any sources that are facing each other, okay? Because in the textbook and in the slides, there is no mention of this. I think that this slide kind of made it in, on accident, right? It's a topic that is not discussed at this moment, so just ignore any sources facing each other, okay? But here you can see by actually just drawing the waves, you can see that they do cancel out at all points, right? All points are destructive. They cancel out. So let's talk about the situation that I want you to study, and that's where you have interference from two sources, and they're facing in the same direction, okay? So here we have a lady named Susan, and she's standing a distance of 6 meters from one speaker and 5 meters from another. The speakers are connected to the same source, so they're producing the exact same sound wave with a frequency of 680 hertz. And at that position that she's at, she's able to hear the sound very well, loud and clear, okay? So that's our clue that at that moment she can hear the sound, and so there's constructive interference going on. But now the point of the problem is that the frequency of the source is slowly increased until she can no longer hear. And so, in other words, the frequency is being changed such that destructive interference is occurring. Right? When she can no longer hear it, that means we have destructive interference of the sound waves. The question is, what's the frequency that this cancellation occurs? And we're going to assume that the speed of sound in air is 340 meters per second. So let me copy this to another blank slide. And let's work on this. So we know that we need to determine what the frequency would be for destructive interference to occur. So let's write our conditions for destructive interference. We know that the path length difference, delta D, must equal some integer m plus 1/2 times the wavelength. And so the speakers have not moved, right? So we can calculate that path length difference, which is 1 meter. And what we also know is how, right, we don't have the wavelength exactly, but we know how to find the wavelength because we know the velocity and we know the frequency, right, and how they're related to wavelength. So let's go ahead and make a substitution. Since we don't care about wavelength, we're going to express the wavelength as velocity over frequency. And so now let's rewrite our equation with everything we know. We know that delta D is 1 meter, and we don't know m, and we know that the velocity is 340 meters per second, and then our frequency is what we're solving for. And so what we're going to do is we're going to solve for frequency in terms of different M's, and we're going to figure out which frequency is going to be higher than 680 hertz. Right? So we're going to solve for frequency. Try different M's to see which frequency is greater than 680 hertz. Why is that? Because the problem stated that the frequency is slowly increased, right? So we know that we're going to get constructive interference at 680, but somewhere above 680, we're going to get destructive interference. So let's do that. Solve for F. Okay, so we're going to try different M's. So let's do F1. We get 1 plus 1/2 times 340. 3/2 times 340 is 510, which is not greater than 680. So let's try our second M. So that's 5/2 times 340. 850 hertz. So that is greater than 680. So that must be what the frequency of the sound is that produced destructive interference when the path length difference is 1 meter. Okay. So that is, one application of constructive and destructive interference, and you're going to see this happen a lot more in the following chapter, chapter 17. So this is a great way to get ready for chapter 17, is understanding this basic situation right here. So if we go back, let's talk about this destructive interference between two speakers. If you have two speakers side by side and you send a wave through speaker one, and it doesn't matter how complicated that sound wave is, you send in some combination of frequencies, and it looks, your sound profile looks something like this, right? If you take that sound profile and you multiply it by -1 through the circuitry inside the speaker, what you'll get is a sound wave that is, equal and opposite to the first one. And if you were to add those two together, no matter how jaggedy and complicated they are, the result would be a flat line, right? 0, no sound. What is this an application of? This is actually what your noise-canceling headphones are doing. So your noise-canceling headphones has some circuitry inside the headphone, and there's also something that is listening to the sound around you. And it takes that sound around you and it multiplies that sound wave by -1 and spits it back out into your ears. And so those two sound waves are going to combine and cancel out any background noise that you do not wish to hear. And so those noise canceling speakers are equipped with some technology that allows voice frequencies to be filtered out so that voice frequencies are not canceled, okay? White noise, maybe from a window being open or from a lot of chatter, background chatter, would get canceled out, but the frequency that is emitted from speaking and voices would be kept. It's a very interesting application. So let's extend this geometry from being, one-dimensional to two-dimensional. If you have a speaker that is not directional, meaning it's not producing sound that is going out in one direction, let's say that it's one of those standing speakers, maybe at a concert, and it emits sound from all around, okay? Then the sound waves looking down at it would look like circles, okay? Where these blue circles here represent the peaks of the sine wave, and they would all line up in different radii. And so when we apply our path length difference, we're simply just going to do slightly different addition and subtraction. So we're still going to apply the same idea that the path length difference, when it equals half a wavelength, you get destructive interference. And when it equals an integer multiple of a wavelength, you get constructive. And so let's look at how it applies to this picture here. The red dot is sitting on intersection of two of those blue circles. And those two blue circles indicate the peak of the sine wave, right? And so we have two peaks adding up, and we know that two peaks adding up is constructive interference. Let's look at the black dot. The black dot is only on one circle, and it's resting in between two other circles, okay? What's in between two peaks of a sine wave? A trough, right? A -1. So there's a trough here, and there's a peak here, right? This blue line represents a peak. And so you're adding a peak to a trough. So you're adding A plus -A. And what do you get? 0. So the black dot is going to be destructive interference. It's just a matter of reading and understanding what these circles are indicating, right? The circles are indicating the peaks of the sine wave, and so directly in between would be the trough of the sine wave. The general rule for identifying constructive or destructive interference is exactly the same. It's just that the way that we are finding the path length difference it has a slightly different geometry. And so this tactics box is basically, if you are looking at a problem and you don't know where to begin, you can literally follow these steps and be able to get the solution, okay, for any kind of constructive or destructive interference problems. Sorry, we have already written on this. Let's look at this quick check problem. And we have two speakers emitting circular sound waves. Okay, let's make this one blue. So the blue circles represent the peaks of the sine wave. The green circles represent the peaks of that sine wave. And directly in between, you have the troughs. So the question is, what is the interference condition at the location of the black dot? Well, so the black dot is located in between both rings, right? The blue ring and the successive green rings. And so basically the dot is located at the trough of the green wave and also at the trough of the blue wave. So what are we adding here? We're adding -A plus -A, which gives us -2A. So that gives us constructive interference, right? Because the peak is getting bigger, it's bigger in the negative direction. And so we're definitely going to have constructive interference here. Let's do this final example. We are Sam is sitting in front of a couple of speakers. Sam is a distance R1 away from speaker 1, And he's also a distance R2 away from speaker 2. And what we know is we know that the distance R1 is 4 meters because he's directly in front of that one speaker. And what we also know is that the two speakers are 3 meters apart, this distance here. So what we don't know is we don't know R2. But we need R2 in order to determine if this is a loud or quiet spot, right? A loud spot would be constructive interference, and a quiet spot would be destructive interference. And so in order to figure out what condition is present there at that location, we need to find the path length difference. So the question is, what is R2? R2 can be found, this is a right triangle, can be found by the Pythagorean theorem. And so R2 is the hypotenuse. It's going to equal 3 squared plus 4 squared. So this is a 3, 4, 5 triangle. So I'm just going to write my answer right here. So we have R2 equals 5. R1 is 4. And so our path length difference is 1 meter. And so we need to check that condition against constructive or destructive interference. And so for destructive interference, that path length difference. Oh my God. Oh, Jesus, so loud. Hello?
Hello.
Hi, what's up?
Nothing.
So let's pick either constructive or destructive to start with. Let's write them both down just as a reminder, right? So delta R is going to equal m lambda for constructive, and then delta R is going to equal m plus 1/2 lambda for destructive. Okay, so let's pick one to start with and see what we get, see if we get a match. So our delta R is 1 meter, and so for constructive interference, that would mean that the path length difference times some integer would have to equal 1 somehow. Well, what is the wavelength? The wavelength we are not given. We need to find it using the speed of sound and the frequency. So lambda f is the fundamental wave equation, so we can easily solve for lambda to b over f, just like we did in the previous example. So 340 over 70, that's going to give us a big clue. 340 over 70 is 2. So since it's 2, we can see that 2 meters, right? We can see that, put our m there, that there is no way to insert an integer in m to get 1 equal to 2. The only way to get 1 equal to 2 is if m, this m here, not the units, m was 1/2, right? So that's already going to give us our clue that this is probably a destructive interference condition. So now if we set up for destructive interference, 1 meter equals m plus 1/2 times 2, right? I'm just going to go ahead and divide 340 by 170. Well, I can get an agreement with the left hand and the right hand side when m equals 0. And so that means that the destructive interference condition is what is happening at Sam's location. So we definitely have destructive interference and thus a quiet spot. This example, I think you should do on your own when you are studying. Try to do it with only the equations available to you without any outside help. It'll be a great preparation, and I think it's very doable. Okay, so that wraps up chapter 16. As always, there's a summary at the end that has some equations and some great concepts. This is a great study area for you. Okay. So look forward for chapter 17 coming up in the next day or two.